Hey everyone, and welcome to our talk. EDR equals erase data remotely, this time reloaded.
And thank you for joining after lunch. You won't regret it. So first we'll introduce ourselves, and my name is Tomer Bar, and I'm the VP of Security Research at SafeBridge. This talk is actually SafeBridge 15 talk at Black Hat. I'm a regular speaker at security conferences all around the world, including Black Hat, DEF CON, and others.
Hey everyone, I'm Shmuel Cohen, and I've been working in the cybersecurity industry for about 6 years now. I began my career as a developer and later moved on to cybersecurity research position, where I did APT malware research. And today my primary focus is vulnerability research at SafeBridge. Back to you, Tomer.
Thank you. OK, so we'll start by introducing our research goal and approach. Then we will detail step by step on how we discover the vulnerability. And then we'll explain and showcase 10 different attack vectors and explain how we bypassed this vulnerability and achieve even a second bypass. And we'll save a special bonus surprise for later on. We'll close the talk with the takeaways, the vendor responses, and the GitHub repository before leaving time for Q&A. So our goal is to be able to confuse EDR products by remotely implanting a malware signature into legit files and making them believe the legit files are actually malicious. For an analogy, Defender usually recognize Taylor Swift as benign, right? So we will try to implant a small malicious mark, and Defender will think that Taylor is actually evil and do his best to eliminate it. So our teaser is, what will you say if we can remotely delete your critical files over the internet without authentication at all, even if you use different security controls or use Windows or Linux fully patched servers? In this next hour, we are going to prove that this is definitely possible. So at the beginning, we had 3 challenges. First of all, false positive or false alarms are known problems, right? For a long time, and security control, which are installed on hundreds of millions of endpoints, are already probably immune to false positive. Moreover, the false positive we are aiming to achieve here are even more rare, since we would like to trigger the byte signature engine, which considered to be the most trusted layer with the lowest false positive rate. And our third and last challenge was how to trigger it from remote. Let's begin. The goal of step 1 is to find a signature that will trigger automatic deletion when appended to our empty file. We decided to use black box approach instead of a white box, and not because it's a black hat, since each security vendor product use a different proprietary database format, and the research goal was to discover as many vulnerabilities in as many products as possible. So black box was the best strategy. We also decided to focus first on Windows Defender. It's the default EDR installed everywhere, right? We assume that VirusTotal use Windows Defender same agent as the regular Windows Defender on endpoints. And VirusTotal also provided us easy hunting capabilities. For example, as you can see, a query for all detected malwares by Microsoft, and we limit it by 200 bytes size binaries. We ran the query and got 3,600 results. We decided to minimize the file to a minimal byte signature that still triggers Defender. Let's go over a simple example to understand our technique. As we can see in the example, we started with the string XABCY, detected signature. We removed the first letter X and wrote the file to disk in order to trigger Defender to scan the file. We still got a detection, so it means X is not a part of the signature. But when we removed the A and wrote it to disk this time, we got no detection. So it's essential part of the signature. B and C were essential too, and Y was not essential, so the minimal signature is ABC. We will use it later. Now we decided to learn more about Defender threat level by reading the documentation. So we found the MP threat class, which includes an interesting field named severity ID. We found out that there are 4 levels of threat severities: low, moderate, and high and critical, and default actions to be taken for each threat severity. We assume that the most severe threat level will probably have a more severe default remediation action, and this is what we look for. And we verified our assumption was correct by reversing Defender. As you can see on the right, this is the logic of the scanner. So our goal is to find a severe level signature that will trigger automatic deletion of our file. We continue our manual search for the right signature, but it took us too much time and failed attempts. So we found a signature that are not required, manual remediation steps, or signatures that causing only part of the file to be removed. So we understood that we should shift from manual process to an automatic process. We downloaded all 3,600 malwares from our original VT hunting query, if you remember, and developed a first basic tool to automatically extract the minimal signature from each malware. The script was very, very basic, just automating the manual process. Large part of the samples were actually a variance of the same malware family, and eventually we found only 130 unique signatures. But how do we select the best signatures for our needs? Since we assume that there are going to be limitations in the implanting of the signature in legit files, we had to prioritize the different signatures in order to find the best signature in the database with the minimum limitations. We believe that alphanumeric signatures will have less limitations. We also might have length limitations, so we would like to use very short signatures. The first signature didn't work. It's a base 64 encoding of ACAR, which Defender only deletes if it's the exact content without extra bytes before the signature or after the signature. So we move on. The second signature, which is only 15 characters length and consists of only 2 types of non-alphanumeric characters, a slash and a curly brackets. Let's try to manually add it to our own empty file. And it worked. This algorithm caused the deletion of our own file. It was actually the first time we managed to find a minimal signature which successfully triggered automatic deletion of our file. But deleting our own empty file is not interesting, right? So our next step was quite obvious, verifying that we can manually append this signature to a target legit file. And we tried to manually append the signature in the middle of another existing document, and for our surprise, it didn't work. So we developed another faster minimizer, which calls Defender scan exported function, instead of dropping each iteration to disk and have to wait for a detection as we did in the first time. This is much faster since Defender does not quarantine files at all in this method. This tool reads the target malware from excluded path and replaces each byte with the letter Z and rescan it. If the value turned to be 9, then we restore it, the Z to the original byte. Let's see an example. We took Mimikatz binary, ran the code, and when we appended Mimikatz signature to the middle of a legit portable executable file, it worked. The problem is we could not think on any interesting attack vectors on PE. If the user already have privileges to write to a PE file, is probably can delete it anyway. So we have to focus on non-executable files and understand the reason why it failed to detect our own signature. We developed additional tool to understand the non-PE limitations. The tool tried to embed the same signature in incremental offsets from the beginning of the file to its end. We found out that in the case of a non-PE file, Defender does not scan the entire file, probably for efficiency reasons. It scans only the first and last 4,030 bytes. So it means that we must append our signatures to those sections in the target file. And if we can do that, we will be able to delete non-PE files automatically. So until this point, we focused on learning how to locally trigger automatic deletion. Now, we should plan how to achieve remote attack vectors. We needed a way to somehow make a privileged device to write our data to a remote file. The first idea that came into our mind were logs. If we will be able to send an HTTP request with our own signature to a web server, and this web server will log our request, we will be able to trigger the remote defender installed on the web server to delete the log file. Okay, but which HTTP field to use? So we looked at IIS logs and saw that the user agent field is a long free text string, which is written entirely to a daily single log file of all client requests, not just our request. So this should be the perfect place to include the signature. So now let's explore our first attack vector. We'll have many. And it's remote deletion of IIS web server logs over the internet. Shmuel will introduce the demo.
Thank you, Tomer. So in this demo, we will see a remote deletion of IIS web server logs. We ran this attack on Windows 11, and for first, I'm taking the IP address of the victim machine, and we can see that we can surf it easily. And let's make sure that our logs was logged into a log file. So navigating into the logs folder, we can see that the current session was logged into the log file. But this time, let's try to attack the machine. So using EDR, which is the tool that will utilize this attack, I'm providing it the IP address of the remote server. And we can see that after running the attack, the log file is no longer available, and Defender detects it as a malicious file. So this log file will be deleted after a reboot to the machine. And as you saw in the demo, and you can see this picture, Defender detects the IIS log as an RTF exploit, and it will be deleted after a reboot. And IIS is a good example for Windows servers. But most web servers are installed on Linux. And in Linux, there is no EDR installed by default. So we aim to trigger other EDR solutions that are likely to be installed on large number of Linux web servers. And as you can see, according to Gartner Magic Quadrant, these are the leading EDR products on the market. We aim at them since they are likely to be installed on enterprise servers. And as you saw, as of now, we confirmed the effectiveness of our technique, and we now have the ability to automatically reduce the size of signatures in a way that would trigger automatic deletion. With this knowledge, the next step was quite obvious. It was to create a database of what we name of evil signature for various leading EDR vendors. This database will allow us to perform signal signature queries capable of triggering most, if not all, of the EDR solutions. This method is beneficial for cases when we don't know which EDR is installed on the remote machine. So we can use this database and get a signature suit for this remote attack. So as we explored different EDR solutions, we noticed that variation in their behaviors, probably caused by difference in their design. However, our investigation led us to discover that Kaspersky EDR demonstrated the exact behavior that we were searching for. Therefore, in the upcoming Linux example, we focus on targeting servers with Kaspersky EDR installed. Another side goal that we had is to find a signature that will trigger most of vulnerable EDRs. It will be perfect for a case when we don't know which EDR is installed on the remote machine. After some tries, we found a signature for triggering Kaspersky, but it also triggered Defender. So let's now see what happens on a Linux machine using an Nginx web server installed and also Kaspersky as an EDR. In this image, you can observe an Nginx server installed on Ubuntu machine, highlighted within the red box. You can see a malicious signature that I'm going to send to the victim. Using a basic Python script, I sent the malicious payload disguised as a user agent to the Nginx web server. And at the moment that I've executed this command, Kaspersky instantly detected the log file as malicious and deleted it. The same method is effective on Apache web servers as well. So in summary, by using a very short signature, we allegedly will be able to remotely delete up to 35% of web server logs in the world. That's pretty amazing results. We've demonstrated this with Kaspersky on Linux, but it could potentially be extended to other security vendors as well. In the following slides, we'll showcase brief examples of various attack vectors that we've identified. The first one will be an FTP server. So not only web server logs are at risk, FileZilla FTP server will be at risk too, for example. This time, by using a signature minimized from invoke Mimikatz PowerShell malware, we used it as a username to the FTP login. This malicious username was written to the FTP logs, which caused Defender to delete it. Another one is an email attack scenario. Using Mozilla Thunderbird, the attacker sends an email to the victim with a subject that includes the malicious signature. Then, as designed, Mozilla Thunderbird stores the entire database inside a single textual file on the disk, and the local inbox will be removed by the EDR, and Thunderbird will try to download it once again. This will cause a non-stop loop of downloading the entire inbox, and then it will be deleted again from by the EDR, and then downloading it back again, and then deleted it again. So another cool vector is by executing a corrupted MSI file. The subject field in the MSI properties will include the evil signature, and this will cause a log record that contains the evil signature to be written into the application Windows event log file, and this will trigger Defender to delete this file. But this is not the end. What about achieving a deletion of Windows logs file, but this time remotely? Is it possible? So the answer is yes. By attempting to perform a remote logging to the machine via an SMB, for example, and using a malicious username, we can remotely insert malicious records into security event log. If we repeat this process enough times, the records will end up at the end of the log file, resulting their deletion. Let's see a demo of it. So again, we're running on latest Windows 11, and this time I'm getting again the IP of the machine, the IP address of the victim machine, and I'm running again with EDRacer a remote attack, this time trying to remotely log in to the machine via SMB with malicious username. And after the script has done, let us scan the logs folder in Windows, and let's see what we will achieve. So scanning the folder, and we can see that it's found something malicious. Let's see what it is exactly. And we can see that this time, the security logs are now considered as malicious, and they will be deleted. Self-cannibalism, how we made Defender delete its own detection logs. It was done from an unprivileged user when even an administrator don't have any permissions to even read the content of this folder. Let's see how we did it. So for start, I'm just creating a new folder on desktop and name it with malicious signature. So this by its own as you can see now, will trigger Defender. Defender detects this as a malicious file. But the interesting part is that Defender will log this incident into its own log files, and now Defender logs file will contain the malicious signature. So if we now scan the logs files of Defender, we will see that, again, it found something malicious. Let's see what it is. So almost all log files of Defender are now considered as malicious, and it will delete its own logs. OK, so now we understand that we can remotely delete logs. But we could achieve even more. Let me ask you a question. What happens to logs on enterprises? Well, as all rivers flow to the sea, all logs flow to a SIEM database. For example, Splunk, which is a central point for monitor, search, and analyze logs. Let's see how we may trigger a domino effect against Splunk. We verified it by manually adding a log file with a name that includes an evil signature. Splunk will write the name of the file to its own database, which will cause Defender to delete the entire Splunk DB. So the same goal can be achieved automatically as a resulting of the domino effect. When an infected Windows event log will be collected by Splunk, it will be added to Splunk database, which again will cause Defender to delete it. Logs are definitely not the only things that we can attack. Let's see two virtual machines attack vectors done under VMware. So for start, we started by taking a look at the VMX file on the guest machine, which is a configuration file of the VM. This file is mandatory for the machine to boot up, and without it, the machine simply cannot boot up again. So we wanted to check if the guest machine can write data to this file in order to implant a malicious signature into it. We searched for a communication originated from the guest machine to the host machine, and after digging a little bit, we found out that VMware tools provide a tool called RPC tool that allows you to communicate with the host machine, and this can be done with a weak user. One of the things that can be done with RPC tool is set global variables. So one of them is called guestinfo.detail.data. So you can set them, these variables, on the host machine, and what will happen is these variables will be inside the VMX file on the host machine. So for example, if you can see this command on the image, I'm setting this guest info variable to be equal to evil request A, which is a malicious signature. So this will bubble up to the VMX file, and it will cause Defender to delete this file, resulting this error. So at the moment that I've executed this command, I got this error on the host machine, and we can see that this error message saying that the VMX file is unavailable, which means that the guest machine cannot boot up again. But wait, there's even more. This attack is nice, but it targets only configuration file. What about targeting the entire virtual data itself? Is it possible? Of course it is. We did it by creating numerous amount of malicious found, around 100,000 files in this case, on the guest machine. And this will cause those files to be written into the VMDK files of the guest machine. And this will cause Defender to detect those VMDK files as malicious, and Defender will delete them. Let's see a demo of it. So running this attack, basically, I put one malicious file inside this folder that you can see right now. So I'm taking from the host machine a malicious file, one single malicious file into this folder. And I'm running this script that will only duplicate this file many times. So after it duplicates this file, as I said, 100,000 times, I'm doing a shutdown to the machine. And we can see that at the moment the machine shut down, we got notifications from Defender, and Defender found out that these files are now considered as malicious. We cannot boot up the machine again because these files are now considered as malicious, and we don't have access to them. And we can see that the machine simply cannot boot up. So the crown jewels of most organizations are not stored in files. Rather, they stored within databases. While we've primarily focused on deleting logs and configuration files, the question arises. Can we potentially delete an entire an entire production database over the internet? So typically, users don't possess the privileges to directly insert queries into a remote database. However, it's common for websites to rely on a backend database for operations. For instance, consider a scenario where a website features a new user registration form. By submitting our malicious data through this form into the database, such as registering a new user, we will have the ability to remotely prompt Defender to delete the entire database without requiring any form of authentication. So let's see a demo of it. So for this demo, I created a small form of registration to a new database, and we're using MySQL as a test database with Linux and Kaspersky installed on the backend. So we can see that the database is actually working, and we're able to insert new data to it. So let's insert a malicious signature to it. So after inserting a malicious signature, as you can see, it's prompted into the database. We can see that Kaspersky immediately detects the database file, the critical database file, as malicious. And we can see that at the moment Kaspersky identified them, we can't no more access to the database. The database service actually crashed. Even if we try to restore those malicious files, Kaspersky again detects them as malicious and deletes them once again, and this database is no longer available. This attack is effective as well on Windows with Defender or other vulnerable EDR solutions. Upon implementing the Mimikatz signature into the MariaDB database, the database file is flagged as malicious. And this not only risks a potential data loss, but it also causes the DB service to become inaccessible, as we saw in the same demo on MySQL. Even attempts to restore it from quarantine or external backup will fail, and we cannot restore its functionality back. We've tested our attack against the most popular database around the world. And in the same way, we were able to remotely delete Postgres, MySQL, SQLite, and MongoDB database on both Linux and Windows platforms with a vulnerable EDR. We're releasing the demos in our GitHub repository. Considering the widespread use of those different databases, the potential impact on major websites is significant. Up until now, we've explored a various remote attacks vector targeting servers and services. Now we'll shift gears and demonstrate the reverse scenario, when a web server can launch attack against a client browser. Let's see how we did it. So when attacker sends a link to a victim, once clicked, the victim browser sends an HTTP request to the server. The malicious web server then responds with a signature, perhaps hidden within a cookie file. As a result, a victim browser logs this response into its local database, which then triggers Defender to delete it. This is an example of remote deletion of Chrome history and the web data database. So we can see that this file is considered as malicious now. We believe that these 10 attack vectors we've discovered are just the tip of the iceberg. And regarding cloud attacks, literally, the sky is the limit. With Defender embedded in numerous critical access points, with Defender embedded in numerous critical points all over the world, and the potential for damage is significant. We reported the relevant vendors at the beginning of 2023, and Microsoft issued a fix to this vulnerability on April 2023, and this is the CVE number. Kaspersky did not release a patch, but they plan to mitigate those attacks as well. But this is not the end of our story, and back to you now, Tomer.
Thank you, Shmuel. So here is the timeline of our findings so far. Immediately after the patch release on April 2023, we started to check the original attack vectors and found out that not all of them were fixed. but we delayed the in-depth analysis to August. So in this example, this is an unpreviewed deletion of Defender detection logs file, which was still possible on fully patched machine by the time of the check, and I can tell you that it's still possible nowadays. After checking out each of the attack vectors we originally reported on January 2023, we were able to see that almost half of the attack vectors are still valid. So on the left is a list of attack vectors that were fixed. And on the right is a list of attack vectors that were not fixed by the patch. So we started focusing on MySQL database, which is one of the most prevalent databases in the world. MySQL default storage engine is InnoDB. The file size is dynamic and enlarged once insertion of new data is reaching almost the end of the file, which the default size is 3 megabytes, causing the vulnerability not to be triggered since our signature is never written to a location scanned by Defender. But InnoDB was not the default storage engine all the time. So MyISAM was the default storage engine until MySQL version 5.5.5. MyISAM database file size is not dynamic, and when inserting new data, it will be appended to the end of the file, and this might be vulnerable. So we give it a shot and try to insert our signature to MySQL using MyISAM storage. Let's see a demo. So in this point, you know the drill. We'll first take the remote IP of the target file. We run MySQL. You can see that it's running. Now let's verify that it's a fully patched machine in the time of the check. Remember, the patch was released on April. We are at the end of July at that point. We run the attack. And immediately, the service is crashed. And we can see that our file, the MYD file, it's the central database file, is detected, and the service is no longer available. Defender detected the MYD file as an MS Office vulnerability and deleted the database file and caused denial of service, as we saw, and data loss. But MySQL 5 is indeed very old. But there were very common installers like WAMP, which stands for Windows, Apache, MySQL, and PHP suite, which uses MyISAM as the default storage engine and made this attack still relevant today. But this was just the first bypass of the patch. But we wanted to be able to bypass MySQL deletion and other databases, even if they use the latest default storage engine. When looking at the table, it's quite easy to see that all the files on the left and marked with green color are stored in binary format, right? And while all the files on the right are stored in textual format. So it seems that the patch changed Defender behavior when scanning a file. It triggers a detection when a textual file includes a textual script-based malicious signature, but it ignores the same signature when the file is in binary format. What will happen if we'll use binary signatures on binary formatted databases? We tried all the signatures we collected from our signature DB using a simple script and found a signature named Levinian case signature, which triggers Defender to delete the database in a fully patched machine. Let's see a demo. So this is an InnoDB MySQL server. So we did it on the same time, the end of July. We'll pick the IP of the target, run the MySQL, and launch the attack. OK, and again, the service crashed. And again, this time, it's Levinian case signature triggering InnoDB files. You can see the InnoDB. And even if you try to restart the service, restart the OS, try to backup from an external backup, it won't work. The database is completely gone. It won't work anymore. So Microsoft released a second patch, CVE 2023-36010, on December 2023. Guess what was our next move? So, of course, we analyzed the patch once again. Let's see what we managed to achieve. The patch did not fix remote deletion of MySQL InnoDB at all. You can see that it's a fully updated Defender on December, included the patch, and the signature was inserted to the DB, which triggers Defender. So let's see if the patch add logic to the MySQL MyISAM remote deletion. Okay, and we found out it indeed was focused on the MyISAM database fix, adding a whitelisting algorithm based on the MyISAM file format. Defender checks if the scan file starts with FD byte and if the file size is aligned to 256 bytes. If both are true, it won't trigger a detection even if malicious signature was found. So our goal is to bypass the whitelist to trigger the deletion of the database file. We don't have control, of course, over the first bytes of the database. So we focus on the size of the record. And the default length value of textual field is 256 bytes. But it's not true for any database that use non-default textual fields length. And according to MySQL manual, as you can see, a text field can reach a length up to 65,000 bytes. What will happen if the victim DB use a non-default textual field? So as we can see, we were able to insert our Levinian case signature into a field larger than 256 bytes in the MySQL MyISAM database file and bypass the whitelisting logic. So we were able to bypass almost all attack vectors fixed by 2 different patches after a year from the original patch and report, of course. So besides bypassing the second patch, if you remember, we promised a special surprise for the end. So we'll introduce how a security fix launched by MSRC introduced a Windows Defender generic detection bypass. If you remember the whitelisting logic that we just showed, added by the second patch, what if we can turn a non-malicious IOC to be whitelisted by Defender due to a security patch? We know that PE files must start with the MZ to work, right? Header, magic. So we focused on scripts. We tried to add FD byte to the beginning of the script, but it, of course, not a legit script command. So we looked for a solution for that, and we found a PowerShell command called error action preference with a possible value of silently continue, which means no effect. The error message is not displayed, and execution continues without interruption. This is exactly what we waited for. And we also added a comment to align the size of the PowerShell size to 256, and comment can be any size, all right? So please meet PowerFD, our tool. The FD gives the malicious PowerShell superpowers to bypass Defender. FUD is also fully undetectable, so it's funny. And it's only 17 lines of code. So you can see all of the 3 steps that we implemented and bypass the patch and make any PowerShell script become fully undetectable. Nice, right? So Microsoft thanks us and confirmed all bypasses, but decided not to fix the last one and not to release the third CVE. Instead, they add improvements and configuration to reduce the risk of false positive and data loss. Here is the full response. Regarding the Defender bypass, Microsoft confirmed the generic bypass, but decided not to fix it, since the attacker must also achieve initial access to the device before the attack. So this is the final timeline. To recap everything, almost all attack vectors are still possible. This is our GitHub repository, where you can find EDR Racer, which supports all the things that we discovered and showcased. And you can also expand new attack vectors very easily. So please use it. I will wait 1 more second to allow you to take a picture. OK, so for the takeaways, and I will conclude with that, remote deletion vulnerabilities are difficult to fix, as you can see, especially when security controls relies on byte signature detections. Security patches might be incomplete Patching should not be treated as a magic bullet, and other security layers should be protecting against a single point of failure. And lastly, security patches fixing vulnerabilities in security controls might introduce bypasses and unexpected behaviors.
Thank you, everyone.
Thank you.